over closed intervals of real numbers. During that video, I started to talk about the ways that mathematicians have tried to expand the class of functions that is integrable, and I removed that discussion from that video because it's a little tangential to proving Riemann integrability. Here then is the discussion I removed from that video on how we can go about integrating functions that are not continuous over closed intervals of real numbers, namely Lebesgue integrals. Lebesgue integrals are sort of the pinnacle of real analysis. The whole last chapter of Rudin's book is on Lebesgue theory. In this video, we'll go over Lebesgue theory in some detail, not rigorous, but enough to really get an idea of how cool and abstract and complicated it is. So in this video, it's about 10 minutes of introduction, about 15 minutes on Lebesgue Measure, and then about 5 minutes or so on the actual Lebesgue integral. The most difficult part of this topic is the measure theory, which takes up most of the discussion. The need to consider more irregular functions has arisen in various ways, and mathematicians have realized that more careful approximation techniques are needed. Okay, so without further ado, Lebesgue theory. Henri Lebesgue is a French mathematician from the late 1800s. He wrote his dissertation on a new method of integration in 1902. So how insane was that? He was still a student when he invented a new way of integrating that is still the pinnacle of real analysis today. And in his dissertation, he said, "The kind of integration defined by Riemann does not allow in all cases for the solution of the fundamental problem of calculus. Find a function with a given derivative. It thus seems natural to search for a definition of the integral which makes integration the inverse operation of differentiation in as large a class of functions as possible." Because Riemann is limited basically to closed bounded intervals of real numbers. So Lebesgue is interested in figuring out if we can expand the class of functions that are integrable. Okay, so this is really cool. I found here Lebesgue's actual dissertation. And this is very interesting. These are the people that are in the faculty of the Academy of Paris where he got his degree. So here's Darboux and here's Poincaré in the faculty of his math department. That's really cool. And then if we look down here, so here right at the beginning, we can see that this is what I just read to you. One knows that there exist functions derived maybe that are not integrable when one adopts, like Mr. Jordan, the definition of the integral given by Riemann. The kind of integration defined by Riemann does not permit in all cases the solution to the fundamental problem of calculus, which is to find a function from its derivative. So it seems natural then to search, that's an E, but I think that's the scanning, that's chercher, to search for another definition of the integral, which in all the cases that we can, in more cases, the integration can be the operation inverse of derivation. So there it is, that's pretty cool. Okay, so anyway. So for instance, the Dirichlet function, Gustav Dirichlet, was a German mathematician who lived from 1805 to 1859, so he's a little before Lebesgue. So the Dirichlet function, it returns 1 if x is rational and 0 if x is irrational. And this is an example of a purposefully pathological function. This function is nowhere continuous, and it is not integrable using Riemann integrals. And in addition to this, so this is sort of a pathological case, there are a lot of other, quote, technical difficulties with Riemann's approach as well. So for one example, the Riemann integral is only defined on bounded intervals, and it doesn't extend well to improper integrals where the limits of integration are minus infinity or infinity. This doesn't work so well. And the reason, of course, has to do with topology, because a compact set has to be closed and bounded. That's what we're going to get to. So this just isn't good for Riemann. And then Riemann integrals also don't work well with taking the limit of a sequence of functions. That makes some very important topics, such as Fourier series, difficult to do using Riemann. You remember in a previous video where we were talking about limits, we proved that if a function f is continuous and the limit of g of x exists, then the limit of f of g of x equals f of the limit of g of x. So what that means is that we could move the limit sign in and out of the function symbol. Something similar is necessary involving integrals in order to work with Fourier series. Basically, Fourier series allow us to approximate any function with arbitrary precision as the sum of a series of sine waves. It's yet another example of our delta epsilon definition, that for any given precision epsilon, we can find a series of sine functions that will approximate the given function to within that precision. And both 3 Blue 1 Brown and Mathologer have great videos on Fourier series that you should watch if you're interested in learning more about them. We probably won't be talking more about them here anytime soon. So to deal with Fourier series, we need to be able to establish that these two integrals are equal. That is, that we can move the integral sign through the summation sign the same way we did with the limit sign previously. But it's proven very difficult to do this using Riemann integrals. And then, interestingly, probability theory also requires integrals with more irregular functions than Riemann can handle. So that's a whole other area of mathematics that requires something more than Riemann can do. And then in addition, of course, one might wish to integrate on spaces more general than the real line, which is what we're looking at with topology generally. But the Riemann integral is inextricably linked to the order structure of real numbers, right? Because we're partitioning the real number system. The Riemann integral is all about the structure of real numbers. So, okay, the point of all this is just to introduce some of the complexities and assumptions that are left unexamined in a freshman calculus class, and to give us more of a sense of just how rudimentary introductory calculus really is. It's the pinnacle of grade school mathematics. When you first encounter groups and fields, you realize that this is what we've been doing all along. Associativity, commutativity. Since grade school, they just never told us so. So the same thing is true of calculus. It's not the culmination of all math. It's the final grade school topic that they're introducing in a simple way that can be useful for engineering and science without delving into what's, quote, really going on. So the Riemann integral isn't powerful enough to integrate all functions. It's good for normal functions, but it has limitations as the math gets more advanced. So in order to conquer the limitations of the Riemann integral, mathematicians have worked to generalize it in various ways. The Riemann integral assumes the standard real line notion of length, but we don't have to take that for granted. So this is again just x to the I minus x to the I minus 1 is the length between these two. So we mentioned a few times in the last few weeks that the definition of a limit assumes a concept of distance, right? Because when we say x minus a is less than delta, what we're really saying is that the distance between these two is less than delta. But we don't have to take that for granted, and one of the goals of topology is to abstract that notion of distance, and in fact abstract the very idea of what a limit is. That's what topology does. But there's a very similar notion of length embedded in the definition of the Riemann integral. And again, we don't have to take that for granted. We can look at that more carefully and see if we can deal with it in a more rigorous way. And we can ask, does the length have to be defined as xi minus xi minus 1? We can apply different notions of length to the width of the subintervals in a partition. This is called the Riemann Stiltjust integral. So Stiltjust is Thomas Stiltjust. He was a Dutch mathematician born in 1854. He died very young, only 38 years old. So instead of just assuming that the width of the rectangle is xi minus xi minus 1, we can define a new function, mu, that defines a new way of measuring the rectangle so that the new size of the rectangle becomes mu of xi minus mu of xi minus 1. So this is exactly the same thing as the Riemann integral. We have the value of f at some sample point in the interval. But instead of just saying that the width is xi minus xi minus 1, we're taking some function mu and taking those values and then subtracting the difference to multiply. So we're just doing this extra step to figure out what the width is, and then what mu is gives us this additional information about what's going on inside this width. So in this context, the Riemann integral is just a special case of the more general Stiltjust integral with mu x equals x, right? So if mu x just equals x, then this would just be exactly the definition of a Riemann integral. So topology abstracts the idea of distance by defining different distance functions, which create different metric spaces, which we'll be getting back to soon. That's what we're going to be doing in topology. This Stiltjust generalization of length opens up an entirely different topic of math called measure theory. So measure theory was developed over time and in stages in the 19th and 20th centuries, in particular by Henri Lebeg. All of this is more application of topology, because measure is defined using concepts like coverings of a set and intersections of open sets and so on, which is what topology is all about. In 1901, Lebeg defined the standard notion of length as a minus b in terms of the more abstract generalized definition of measure. And this measure theory definition of the standard notion of length is now called Lebesgue measure. And then he used this concept of measure in order to define his new way of integrating, which is called the Lebesgue integral. So as Lebeg stated in his dissertation, the goal of both Stiltjust and Lebeg is to extend the usefulness of Riemann integrals as far as possible. The basic statement of the Riemann-Stiltjust integral was actually pretty straightforward. The Lebesgue integral is far more abstract and advanced, but at the end of this video, we'll show how to define a Lebesgue integral in terms of Riemann integrals. So before we can look at the Lebesgue integral, we have to look at Lebesgue measure. Remember, this is only for fun. It's just to get a taste of where real analysis is headed. We don't need to worry about understanding it in detail, but the actual definition isn't that hard to follow, and it's another example of how math can go off in wild directions and how primitive our freshman calculus class really was. Okay, so Lebesgue measure. So metric spaces focus on measuring the distance between 2 points. Measure theory focuses on something a little different relating to area. Measure includes, in some sense, how dense or how connected or compact the space between the points is, or maybe how thick the points are. So that is, the measure of the closed interval in the real numbers from 0 to 1 is 1. But the measure of that same interval over the rationals is 0 because of those gaps in the rationals that real analysis is so obsessed with. So if we have an interval, it looks like a bunch of points, right? But between any 2 points, there is an irrational number. So this is what we've been talking about from the beginning, that there are gaps in the rational numbers. And as a result, the measure of this same interval over the rationals is 0. Even though rational numbers are dense in the reals, there are still gaps between them. So every individual point is infinitely small in some way, and so it has measure 0. Measure theory is about characterizing the width or the thickness of the points and the gaps between. And remember, Lebeg's goal here is to expand the notion of an integrable function so that it's maybe possible to integrate some functions that even have infinite discontinuities. So to define Lebesgue measure, we start by defining the length of an interval in the real numbers in the usual way. So for any interval I from a to b, let L of I equal b minus a be the length of that interval. The question is, how does that concept apply to arbitrary subsets of the real numbers? What can we call the length of a set in that sense? So for any subset E inside R, we're going to cover E with a set of open intervals. And see, so we're looking at coverings again. We were just looking at this last week with compact spaces. Now here it is again. The Lebesgue outer measure, which we'll call lambda star of E, is defined as okay, looks really complicated, doesn't it? So we're taking the infimum of something. This is the length of an interval. We're taking the sum of all of these intervals from 1 to infinity, where ik is a sequence, k is a natural number, of open intervals with if you take the union of all of them, then E is a subset of that. And we're taking the infimum of that. So what this means is that we're taking all possible coverings of E with open intervals of R. I defined the Lebesgue outer measure like this, and I really dislike this notation. This is the way that Rudin talks about it, and this is the way it is in Wikipedia. But I think it's very confusing because when they say that IK is a sequence of open intervals, then the sum, each element of this set is the sum of all of the i's from 1 to infinity. So that makes it look like the k is, that each ik is a different element that's being summed up. But over here, ik means it's a sequence. But you don't take the sum of the whole sequence, you're summing it from 1 to infinity. So I'm going to rewrite it here more clearly. You don't get credit, you don't get points for brevity, you get points for clarity. So we're going to rewrite this definition more clearly so that at least what this is saying makes sense. And I think after I've rewritten it, you'll be able to see what this is really trying to say. And then I think that it's not wrong, it's just not at all clear. So we're gonna write it clearly and then we'll go back to talk about what this means. Okay, so we start the same, defining L as the quote length of an interval of real numbers. For any open interval of real numbers, I, from A to B, let L of I equal B minus A. For any subset E of the real numbers, we consider a countable covering of E by intervals ik, where k is a positive integer, such that E is a subset of the union of all of those intervals. Okay? So this is a description of one sequence of intervals that covers E. So let P be the collection of all such countable coverings. Let AI be an element of P. Okay, so A is one of these coverings, and then P is the collection of every possible such covering. We'll use I sub ik to refer to the kth interval of the covering AI. Okay, so A is one of these coverings, and then P is the collection of every possible such covering. So let mu of AI be the sum of the length of every interval in A. So AI is one of these coverings, and mu AI is the sum of the length of all of the intervals in that covering. Then the Lebesgue outer measure equals the infimum of the mu of every element of P. Okay? So with all this in mind, you can see what this is about. They're using K in two different ways. So this is a description of one sequence of intervals that covers E. The confusion is, it looks like they're using I sub K in two different ways. The parenthesis I sub K on the right is a sequence. But then that sequence isn't referred to explicitly in the sum, so you have to really fill in a lot of blanks to figure out what's going on. The sequence IK on the right side is the thing that's being summed up, one sequence at a time on the left. So one element of this set is the sum of the lengths of all of the intervals in one covering. And then we're taking the smallest one, the infimum, that's the outer measure. So what this means is that we're taking all possible coverings of E with open intervals of R. So E can be anything. It can be intervals, isolated points, a union of disjoint sets, and so on, okay? So this could be E. So we're taking every possible covering of this set by open intervals of R. So one covering could be one big interval, one could be a bunch of little ones, one could be a sequence of nested intervals where each one's a superset of the one above it, like that. Or one might be a sequence of overlapping intervals, something like that. So every possible sequence of intervals that covers E is included in this set. So for each one of these coverings, we're taking the sum of the lengths of each of the intervals in that covering. So here it would be this plus this plus this plus this. Here it would be this plus this plus this plus this, and so on. And then we're finding the infimum of all of those sums. So E is a subset of the sequence of intervals. So that means that the covering may include points that are outside of E, right? The covering could be bigger than E. And another covering might have intervals that are overlapping. So when you take the sum of the lengths of these intervals, some areas might be counted twice. So in both of these situations, the sum of the lengths of the intervals is too big, either counting extra points that are not in E or counting the same points twice. So what we're looking for is, out of all the possible coverings of E, the one that fits E the tightest, with the least extra and the least overlap. And that's what the infimum of the sums give us. In other words, we're looking for the total length of those intervals that fit E the tightest. Okay? That is the Lebesgue outer measure. So to define the Lebesgue measure proper for the set requires an additional condition. Take another set, this all gets very strange, but take another subset of the real numbers, and then we use E to divide A into two pieces. So if this is A and this is E, so we have the set A, and we're going to use E to cut A into two pieces. So it's the part of A that intersects with E is here, and then the remaining part that does not intersect with A, which is out here. Then what we do is we take the outer measure of each one of these chunks, the intersection and the difference. So this is A intersected with E, and this is A minus E. And by the way, the next video is going to be, we're going to start with the basics of set theory so we're all on the same page. So I'm going a little out of order here, but A minus E means everything that's in A that's not in E. Then, with the outer measure of each of these, we compare the outer measure of each of these to the outer measure of A as a whole. So in other words, we're going to take the outer measure of A as a whole, and we're going to ask whether the outer measure of A as a whole equals the outer measure of these two pieces. So we have the outer measure plus the outer measure plus this. Okay? Now, if for all possible subsets A of the real numbers, the outer measure of A is the same as the sum of the outer measure of the two pieces split by E, then the outer Lebesgue measure of E is in fact the Lebesgue measure of E. So if this is equal, then the Lebesgue measure of E equals the outer measure of E. How's that for insane? And remember, what are we trying to do here? We're trying to integrate. We're trying to integrate some functions. This is totally crazy. What this is about is checking whether E has some curious property that causes a discrepancy in the measure of another set when we use E to kind of mask or clip the other set. So if there's something weird about E so that its outer measure does not fit tightly over it, then when we're using it to cut A, there might be some overlap that prevents us from cutting A cleanly. But if the two sides of this equation are equal, it means that the outer measure fits E tightly and there is no overlap. So we can call the outer measure of E the Lebesgue measure of E. So it's almost like, the way to think about it is if you're familiar with Photoshop at all, like if there's this set if it's fuzzy in some way, it might not be clear what's cutting this, and it might be cutting A in a way that makes these two pieces fuzzy as well, so that then the outer measure of these two has to kind of be a little bigger. They don't, like, so that E kind of cuts it in a way that makes the two pieces of A fuzzy as well, so that the outer measure has to be bigger than if you just took the measure of the whole thing. I think everything we've looked at up until this point, I have felt is graspable. Like, I can see where the mind was coming from that came up with these concepts. There's a level of vision about how these sets work here that is beyond me at the moment. To think, to see that this is what the issue is, this is what the problem is, and the way to test it is to cut this with another one, and then we'll be able to tell whether there's something wrong with E. We're going to use E to cut another set, and if that set gets messed up by cutting E, by letting E cut it, then we'll know there's something wrong with E. And by the way, don't forget, it's not just a set. This is every set. We have to, in order to use this measure, we have to find some way of testing that every subset of R is cut cleanly by E. So I think we can get what it's about, but the details will be very difficult. So we're just glancing at this right now. I don't know whether we'll need to come back to it for Fermat's last theorem. Okay, all of this was so we can define an integral that can integrate a wider class of functions than the Riemann integral. So the Lebesgue integral. So the Lebesgue integral is a completely novel way of doing it. So Riemann took a function and cut it up vertically. What Lebesgue does is take the function and cut it up horizontally. Now, what's funny is, if that's as far as I explained it, you're like, oh my gosh, Lebesgue was brilliant. He rotated at 90 degrees. Who would have ever thought of that, right? But the weird thing is that if this is all you hear, you're like, what is the big deal? But there's so much more going on here. There's a reason for this that's so much deeper than just, hey, let's try it this way. Because his real insight is that we should be able to rearrange the values of a function freely while preserving the value of the integral. So here's what he said in a letter to another mathematician, Paul Montel, about his approach to integration. So he says, I have to pay a certain sum, which I have collected in my pocket. I take the bills and coins out of my pocket and give them to the creditor in the order I find them until I have reached the total sum. This is the Riemann integral. But I can proceed differently. After I've taken all the money out of my pocket, I order the bills and coins according to identical values, and then I pay the several heaps, one after another, to the creditor. This is my integral. So in other words, Riemann takes the money out of his pocket one at a time, and whatever it is, gives it to the creditor. Lebesgue takes all the money out of his pockets, then sorts them into piles of quarters, dimes, nickels, and pennies, and so on, and then gives the creditors the quarters first, then the dimes, then the nickels, and so on. And this process of rearrangement, this isn't a good example, because it can be, the purpose here is that it can be a lot more complicated. Because if you do it this way, you're taking the total value of each slice as it goes and collecting them and then adding them together. Whereas Riemann just had to take it as it comes. So this process of rearrangement can convert a very pathological function into one that is nice from the point of view of integration, and thus let such pathological functions that are not integrable under Riemann be integrated with Lebesgue. The Dirichlet function that I wrote down before is not integrable using Riemann integrals, but amazingly it is integrable using Lebesgue integrals. So, okay, how does it work? So we start with a measure for the domain of the function, which we call mu, m for measure. So this measure associates to each set of real numbers a non-negative number, mu of a, representing the size of a. So this notion of size should agree with the usual length of an interval or a disjoint union of intervals. So if this is just a straightforward interval from a to b, then mu of A should be the same as just taking B minus A. So we're not just abstracting the notion of size. What we're doing is extending the notion of size. We're assigning size to sets that are possibly irregular. So if it's a normal interval like this, we know what the size of this is. It's just B minus A. But if it's something more strange, like the Dirichlet function, we're still going to assign a size to even those sets. Okay, so if we have a function, so if we have a value t, so what we want to do is take a strip here below it. So this is dt, and then take the area. So what we want to do is to take the sum over t of the area contained in the thin horizontal strip here between y equals t and y equals t minus dt. Okay, so dt is a small change in t, so it's from t minus dt up to t. So then dt approaches 0, okay? So it gets thinner and thinner, and then these strips get thinner and thinner. So remember, we can take the measure mu of any subset of real numbers. It doesn't have to be a continuous closed interval. So even though the chunks of the strip might be disjoint, that's okay because mu represents the measure of any subset of reals. So the area of one strip then is just, so this is the set of all x that has f of x bigger than t. Okay, so t is going across here. From here to here, f of x is bigger than t. But then here, f of x is below t. So these x's are not in the set, these x's are, these x's are. Okay, so this is all of the x such that f of x is bigger than t, times dt. So even though what we're looking at is the stuff above, that's not what we're calculating. We're calculating the size of this rectangle here, which is all of the x's that have f of x above t times the width of the strip, which is just dt. So it's just like Riemann. It's the simple area of these rectangles, but it's the total width of all the rectangles in each strip added together. So then, with this in mind, we let f star equal the measure of each one of these sets. So then, as t goes up and down, the total size of the strip is going to change, right? As it comes down here, then, if it's down here, then all of the x's from here to here are in it. So it would be the measure of this whole thing. But then as it goes higher, it's smaller there, but then you're still taking the measure of the total set of x's that have f of x greater than t. Okay, so the Lebesgue integral is defined as the integral of f d mu equals the integral from 0 to infinity of f star of t dt, where the integral on the right is an ordinary Riemann integral, except it is improper because the limit of integration goes to infinity. We're not going to be looking at improper integrals much, but it's okay that one of the limits of integration is infinity here because f star is a non-negative decreasing function, right? Because as t goes up, the measure of the set that is still counted is getting smaller and smaller. So if the function has a measure, then f star has a well-defined improper Riemann integral. Do note that it might still be divergent, so the integral might not have a defined finite value. So isn't this amazing? Lebesgue actually managed to find a way to use Riemann integrals to integrate functions that cannot be integrated using the Riemann integral. That's amazing. So how is the Lebesgue integral different from Riemann? The Lebesgue integral can handle functions like the Dirichlet function, which is discontinuous everywhere. So here's the Dirichlet function. So it's 1 whenever x is rational, and it's 0 whenever x is irrational. So infinitely many times it goes up and down like this. It's discontinuous everywhere. Riemann can't handle this, but Lebesgue can. And the real problem for Riemann is that the Riemann definition requires an open interval around each point in order to get the value of the slice as it's getting narrower and narrower. But the Lebesgue integral does not. So even though each point in the Dirichlet function is discontinuous, Lebesgue measure is able to measure these sets. The set of rationals in the reals has measure 0. It's a collection of infinitely thin slices. So it's one here, one here, one here, but none of them have any thickness. They don't even have any thickness as you approach them. Like there's not even a limit. They're not continuous. It's just this one slice, but there's gaps between, there's infinitely many gaps between them all along. So the measure of the rationals in the reals is 0. And this is what the Lebesgue integral is able to capture. So the Lebesgue integral for this function exists and it equals 0, which is exactly what it should equal because the area of all of these infinitely thin slices is 0. We're never able to get any substance to them. And that's what measure is all about, really honing in on what size means. Even though rationals are dense in the reals, their measure is 0 because there are no two rational numbers together to make any width to the rectangle. Anyway, this is all getting very advanced. The last chapter of Rudin's book is entirely on Lebesgue theory. We're not going in that direction right now, but it's very cool. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.